Hello, Calculus. The day you're watching this is after class on Tuesday, so it's the 20th, and we're going to investigate infinite limits. And we've kind of danced around this, so I'm sorry you get a homemade video tonight. I didn't get around the chalkboard when I had a chance, so do the best I can with paper and pen. Let's see, suppose we have this graph, and I think we had something like this on one of our problems when we were just looking for limits graphically, and it became asymptotic above, but right here this point existed, and this became asymptotic to this side. So it looks something like that, and the problem asks us what the limit was as x approached c. So we looked from the left and the right, and we saw they both were going upward, and we said it was infinity. And remember, the book said no, it said it had no limit. So we're just going to fine-tune that idea. And the reason we said that I said it had no limit, when I got to thinking about it, when we had our delta epsilon definition of a limit, it said L was a number. And if you look back at that definition, and infinity is not a number, so that's why we come up with the no limit idea. So we're going to fine-tune that a little bit tonight. Alright, so let's look at this one. It says the limit as x approaches 2 from the left of 3 over x plus 2. So have you been well taught? You should have remembered how to graph this. And the parent function is 1 over x, so that's what's in your mind. But this will cause it to vertically shrink or stretch, and this will cause it to go left. I'm sorry, you would think it would cause it to go left, but it's a hugger, so it's going to go right. So here, sketching it, we're going to have a asymptote at 2. And also, we are going to remember it's a slash type of thing, because there's also a horizontal asymptote, case 1, where the degree of the denominator is higher than the degree of the numerator. So we did give ourselves a sissy chart, and if we just put in one value, like 0, we get -3/2. So that's down here. So that tells us our slashes have to be this way and this way. Alright, so that's how we used to come up with the graph. So hopefully that's still looking familiar to you. So this graph becomes closer and closer to the asymptotes. So back to our original problem, what's the limit as x approaches 2 from the left, coming in this way? Do you see we're increasingly going further down, closer we get to 2. So the answer to that is going to be negative infinity. When we say negative infinity, you might be confused. Why do you say, because we're coming from the left. If I said if we were coming to 2, we'd say there's no limit because it goes up one way and down the other. But coming from one side and seeing that it goes down forever, we say negative infinity, but we are not calling that a number or a specific limit. What that means to everyone is it's decreasing without bound. And we are allowed to call that limit negative infinity. Let's look at the same problem coming in from the other direction. So this is a plus sign there. The limit as x approaches 2 from the right is going to, as we get closer and closer to 2, we see this function going up. So we can say in like manner it's positive infinity, and again that means increasing without bound. Alright, so when we say that, we're not talking about a number, we're talking about a concept. Let's rigorously find the definition of infinite limit. So this will look familiar. I'm not going to ask us to do delta epsilon proofs, but I do want you to have seen the definition. It won't be too shocking after what you've been through. Let f be a function defined in an open interval containing c, though possibly not defined at c. We have those badly behaving functions. The limit as f of x, as the limit as x approaches c of f of x equals infinity means. All right, you can stop this video and catch up with this definition, but I'm going to keep going. If the limit as x approaches c of f of x is infinity, that means for every m greater than 0, there is, what is the word is, sorry, there is a delta greater than 0 such that whenever 0 is less than the absolute value of x minus c is less than delta, then, I was going to try to drag it out of you. So what are we trying to say here? Can we look at a picture and see? All right, here I drew a picture of something, since I'm trying to find the limit or the definition of a limit when it goes to infinity at c, as we approach c. So I drew a c and one that would approach infinity. So that means for any m greater than 0, so let's just say you choose a number m that's really, really big. So maybe it's up there at 1,000 or even 1,000,000, just a big m. No matter how big, you pick the m, there is a delta greater than 0 such that, remember what this meant? This meant that my x values were within delta of c. So I'm going to create an interval. I'm going to go c plus delta and c minus delta. And can you see what would follow then? In order for this to have an infinite limit, what's going to happen when I restrict my selection of my x values to be close to c, within delta of c? Then what's going to happen to the function if indeed this is the limit? F of x will have to be, what's going to happen as I get closer and closer to c? Can you see it's going to go up and up, and it's going to be greater than m. So no matter what m you pick, I can find a delta that will give you the function greater than m if the limit is infinite. All right, hope that picture helps and that you were able to fill it in before I did. All right, see if you can do it the other way. All right, now let's talk about negative infinity. The limit as x approaches c of f of x equals negative infinity means for every n less than 0, so this time I'm picking an n that's way low, like maybe negative 1,000. There exists a delta greater than 0 such that when, I didn't give you much, did I? When can you do the if-then part? The first part is the delta part. 0 is less than or equal to something which is less than something. Should look familiar. When my x value is within delta of c, so that's how I say that in absolute value language, then f of x, no matter how small I make this, is going to be less than n, if indeed the limit is negative infinity. All right, I won't tease you anymore with that. Let's just go on. and see what the first example is. I want you to find the limit here that I've asked you to find. And we're going to pull out the algebra and use some of our old techniques. So factoring the top, I'm going to get x plus 4, x minus 2. On the bottom, x plus 2, x minus 2. So this crosses out, but I'm still not allowed to use the value 2 because it would cause this denominator to zero out as what it is. So we cannot let x equal 2. So do you remember what happens when it's not a 0 and it's not an asymptote? This creates a hole in the graph. This will create the asymptote at x equals -2. So let's just see if you remember some of that skill. So we put in our graph and we're going to recognize it has an asymptote at -2 because of this factor in the denominator, and we're expecting a hole at x equals 2. So and there's, because this is the same, what do I have written here? Oh yeah, since this is the same, this case 2, this is the same order as this. So same, the exponent here is here. So therefore, remember, we took the coefficient of the numerator, the lead coefficient in the numerator, and divided it by the lead coefficient in the denominator, and found out that our y asymptote was 1. So now which way does it go? Slash slash or slash slash? A quick sissy chart at 0. When I put 0 in this function, the original one, I get -8 over -4, which is a 2. So I graph 0, 2. So that tells me all I need to know. When I get to the x value of 2, I put in a hole, and like that. Alright, that was a blast from the past. So now that you've got the sketch, can you find the limit? As x approaches 2 from the left, you can see it goes continually lower. So we're going to get a limit as x approaches 2 from the left, we're going to get -infinity. So this equals -infinity. All right. I'm going to shut it down and come back with part 2.